is the video for section 1.1 of our book. This is the section that is introducing basic functions and basic notation that we'll use throughout the course. Before I start, let me tell you about what calculus is. So up to this point in mathematics, you've been probably studying college algebra-like topics like solving equations, plugging things into functions, drawing graphs, or trigonometry kind of things like the sine function, the cosine function, unit circles, triangles, and things like this. Calculus is a very different kind of mathematics from those two. In calculus, fundamentally we're concerned with how things change. You can say in short that calculus is the study of change. And what do I mean by that? So there's two senses in which calculus studies change. The first sense is what you see here. So this blue line is the parabola, y equals x squared, and this green line is a very special line that touches this parabola at exactly one point, at the point 1, 1 that I'm hovering on right here. And what it has the property of is that it touches at that point, and it essentially touches it and moves on away. Now, what do I mean by that? I mean that it doesn't touch it in two places around that point. So its function sort of balancing exactly on, or this linear function is balancing exactly on this quadratic function, and it's called a tangent line. Now, when you studied slope in college algebra, you were finding slope of linear functions, so you could find a slope of this green line. But calculus allows us the ability to find slopes of curves. So the slope of the curve at this point 1, 1 is the slope of that green line, and then we use the formula for the equation of a line to find the green line, and we will do this soon. This is called differential calculus. Now, this is kind of a abstract geometry problem, but you will see that this gets its fingers into all kinds of scientific areas, and it is very, very applicable kind of mathematics. That's half of calculus. So, the way this course will go is we will study something called a limit, and then we will move on to differential calculus, so these linear functions that are making tangent lines to curves, and then later we'll do integration. And the punchline of calculus is how all this is related to each other. Now, the other half of calculus is integral calculus. So I have some kind of blue line here, and what I'm interested in is not finding tangent lines to this curve, but rather just the simple idea of finding the area under the curve. Now, if this curve was a horizontal line, you could, use length times width, the formula for a rectangle, to find the area, no trouble. But this is a curvy thing, and so we need to develop tools to do this. So this thing I mentioned earlier called a limit is what we use in both of these cases to define what we mean by these operations. So this derivative thing, this slope that we will find here, we will find it by taking slopes in the college algebra sense and then taking a limit of them, whatever that means. And with these areas, we will use little rectangles under the curve and then take a limit, and that will somehow give us some well-formed notion of area under the curve. And so that's why in this course we'll first fundamentally this week study functions, but soon we'll start limits. These limits become the basic operations of calculus, and then we will look at how these operations are used in various areas of science and social science and things like this. So for now, I think that's a pretty good overview. Let's just dive right into section 1.1. That way we can get through this. So for some preliminaries, when I draw this symbol R, you may know the symbol already, but what I mean by this is the number line. So, the horizontal line with 0 at the middle, positive numbers to the right, negative numbers to the left. When I write this notation, I mean a line segment, and the fact that I'm using these sharp brackets indicates that I'm including the endpoints in my interval. So if I don't want to include an endpoint, I'll put a parenthesis there. And so you should be used to these things, but I just want to make sure we're all on the same page. Now this notation will just be present throughout the whole class. Okay, so calculus fundamentally is the study of certain functions. So let's remind ourselves what a function is. Now, in college algebra, to you, a function is something that you plug numbers in and you get numbers out. So we're going to think of a function sort of a little more precise occasionally than that. So this is my favorite way to present functions. A function's 4 things. 1, we give it a name. So something like f is a pretty good name for a function. It's usually the most common. We have a domain. So these are the set of inputs that we're allowing. So when in college algebra they say, find the domain of the function f of x equals x squared, and you report to the professor that the domain is all real numbers. Well, that's kind of backwards from how actual mathematicians and scientists use functions. When we use them, and we want to say it's a function, we have to specify what domain we're talking about. So it's occasionally useful, as you may have seen in trigonometry, that the full range of the domain, range, that's a pun, the full size of the domain is not useful if you want to define something like an inverse sine function. An inverse sine function requires a domain restriction to make the function what we call one-to-one, therefore there's an inverse. Now all that's usually brushed under the rug in a trigonometry course, and they tell you, the allowable inputs to inverse sine are this, and the outputs of inverse sine are that. And that's the end of the story. But as you go along and get more mathematically mature, you will find more and more uses for this full definition of a function, and we will use this occasionally in here. So that was number 2. Number 3 is a codomain. Now, codomains is slightly different than the range. I think most college algebra courses will talk about the range and ask you to find it. But the codomain is just where the range lives. So sometimes the codomain is the range and sometimes it's not. I don't think the codomain is going to be super important in this course, but when you get to something like Calculus 3, it becomes more and more important, and especially in higher level math, it's very important. In Calculus 1, we can usually get by without worrying about the codomain too much. It'll generally just be the real numbers, because all of our functions will more or less take real numbers as inputs and give us real numbers as outputs. Finally, a function has a rule of assignment that associates each thing in the domain to precisely one thing in the codomain. This is your f of x equals x squared plus 3 kind of thing. And that's usually when you see a function, that's the thing you're given. You're given the name, number 1 and number 4, and number 2 and number 3 are sometimes brushed under the rug. And I will be guilty of that as well from time to time. So in case I do use the full generality of a function here, I will write it this way. I'll have the name of the function, I'll put a colon, and then I'll put the domain, and then I'll put an arrow, and I'll put the codomain. And the rule of assignment will be what you're used to, this f of x equals something or another. So the only other thing, the most important thing maybe for us, for functions, is drawing them, because functions will be the object that we use in calculus to do these derivatives and integrals that I mentioned earlier. So when you graph a function, what do? Let me just remind you. So this is a function where I've defined the domain to be -1 to 1, and that's why the x-axis is from -1 to 1, and the codomain is 2 to 4. So I'm only considering this output space. And the function itself is f of x is x plus 3. Now when I plot this function, what do? I plug in all the domain values. So say I plug in -1. If I plug in -1 into this function, I'm essentially setting x equal to -1. And what that does on the right-hand side, it gives me a nice arithmetical formula, -1 plus 3 which is 2. And so the x value minus 1 is associated with the f of x value 2. And that's why we plot this point minus 1, comma 2. Same thing over here at 1. If I plug 1 into this function, x will be 1. 1 plus 3 is 4. So that's why this point is the x value 1, comma, the y value, or the f of x value, 4. Now that's something to mention, by the way. Y values and f of x values mean the same thing. And your college algebra course should have hit on this, but sometimes it does not. So f of x is the y-axis and x is the x-axis. So sometimes, like I mentioned, functions will be given without a domain specified, and this is very common. So here's an example. Here's f of x is 1 over 1 minus x. So when you're presented with such a thing, you should just interpret it as its maximal largest possible domain. Now what we have here is a problem. When we have square roots or we have division, we have to avoid two things all the time with functions in Calc 1. These are dividing by zeros, a no-no, we cannot do it, and we cannot take square roots of negative numbers here, although you may have seen in college algebra that this is possible to define. It leads you to the imaginary number and complex numbers and things like this. But this course is about real variable calculus, not complex variable calculus. So we will avoid complex numbers here, but be aware that there are courses out there that do talk about complex value calculus, and they're very interesting. But you have to start somewhere, and real value calculus is a nice starting point into all of this. So when we want to find the domain of this function, we ask ourselves, are there any square roots? In this case, no. Are there any divisions by variables? In this case, yes. So we find out where that denominator is 0, and we throw it out. And that's what I say at the end here, that the domain is R, and I have this backslash, and then I have the set containing 0. And that's notation in set theory for, I have the whole real line, the number line. Oh, I shouldn't be subtracting out 0, I should be subtracting out 1, right? So that's a typo. It should be R take away 1. But that's fine. What that means is I have the whole real line, but I do not include the point 1 in it. And there's other ways to notate this, like the interval from minus infinity to 1 with a parenthesis on the 1, and then union parenthesis on the 1 to infinity, and that's acceptable too. If you even want to write words, if you want to write in as a sentence, the domain is the set of real numbers without without 1, that will be acceptable. All I care is that you can express to me what the domain is when it's needed. Let's look at this function, by the way. So this is Desmos. You may have seen it before. It's a nice plotting tool for things. So if you go to Desmos, let me just go there right now. You click Start Graphing, and you're presented with this window with these boxes. And so I want to plot this function. Now, like I said earlier, f of x is another name for y. So if I just type y equals 1 over 1 minus x, ta-da, we get this nice graph, and we see that this point at 1 is something strange is happening there, right? It's what we call a vertical asymptote. It's this place where the function will not cross, because for the graph to cross it would mean that we'd have to be able to plug 1 into the function. And we cannot, because, well, it causes a division by 0. So the consequence of this for the graph is that the graph will get closer and closer and closer to 1, but it'll go towards positive or negative infinity, depending on what side it comes from. And that's the only thing it can do, and to kind of get closer and closer to 1, but not actually touch it. Now, you could say, well, what if the function came in like linearly, and it skipped 1 and then went onwards? Well, that's valid too. That's a different function. But this function, the division by a variable, causes this thing to get very big. So, I mean, that's just the function. So, there's a good example. Okay. So in calculus, important thing is the ideas of increasing and decreasing. And so we have this formal definition here about if you have 2 points on an interval and they're one smaller than the other, and you plug them in, what do the values of the functions do? I mean, this is a pretty obtuse kind of definition in the sense that it's hard to work with. It's useful, and you can work with it occasionally, but most of the time we will either plot a function and visualize where it's increasing or decreasing, or once we get derivatives, we will be able to just calculate this out on paper. But at this point, increasing should mean to you, if you're moving on the x-axis to the right. Let me draw a picture. Let's look at this first example. F of x is x squared. Now this function is not increasing everywhere and it's not decreasing everywhere. So what do I mean by that? Well, I mean, if you're at, say, -3 on the x-axis and you head to the right, you're walking to the right towards 0, then you see that the graph of the function is going down. It's going down, it's going down, and that's what we mean by decreasing. It means as you read it left to right, the function is moving in a downward direction. So once you're at 0 and you start going further to the right and you go along the function, you notice now you're going uphill, and that's what we mean by increasing. So this question, this example, it asks, where is the function f of x is x squared increasing and decreasing? Well, it's decreasing at all negative real numbers. So if you wanted to write it as an interval, you would say minus infinity to 0, and you would put a parenthesis on the 0, because at 0, it's neither increasing nor decreasing. So when we're talking about increasing and decreasing, we want to use these open intervals that do not include endpoints. Now, where is it increasing? It's increasing on the positive numbers, so you could say the open interval 0 to positive infinity. And that is it. This function decreases on the left, increases on the right, and that is it. Of course, we can have much wilder behavior. I mean, you've seen in trigonometry, say, sine and cosine functions, they go and oscillate forever. They increase and decrease alternatingly ad infinitum. So usually we will end up calculating these using basic calculus. Let's look at this other example. So this is the function x cubed minus 5x plus 2. Plus 2. So here it is. So if you zoom out, so you use your mouse wheel and scroll down or pull backwards on your laptop or zoom out on a phone, you can get this to appear. Now this is a little more interesting of a graph because it seems like we're increasing until we reach this peak here, then we're decreasing until we reach this valley, and then we increase again until we go on to infinity. Now at this point, I don't expect you to find the coordinates of exactly where this peak occurs, because that's something we will do. So if I give you a question like this in homework, and you can't find the actual numerical value where this peak occurs or where this valley occurs, what you can do is you could say draw a picture of this graph and then indicate on the x-axis where it's increasing and where it's decreasing. I just want you to be able to identify increasing as opposed to decreasing, because this is a big deal in calculus. Alright, the only other thing in section 1.1 that we're going to talk about is composite functions. Now, composite functions are the idea of combining two functions together by plugging one into the other. And you've seen this in the past, so I'm not going to spend a lot of time on it. But later when we're doing what's called the chain rule, this will be very, very important for us to identify, but not in the forward direction of computing a composition, but rather in the backwards direction of identifying a composition. But for now, let's just talk about computing a composition. So in this example, I have f of x is x squared plus 3, and g of x is 1 over x. So there's two composite functions you can make. You can take g and plug it into f, or you can take f and plug it into g. And that's the two situations we have here. So I have f of g of x, and so when I want to compute this, what do? I replace g of x with what it is, and in this case that's 1 over x. So the formula is telling me compute f of 1 over x. Well, what does f do to an input? Now this formula, f of x is x squared plus 3, is telling you that f is the function that squares whatever you feed to it, and then takes that thing that you got when you squared whatever you fed to it and add 3 to it. So since down here, when we're computing f of g of x, we are computing f of 1 over x, the definition of f is telling us to plug in 1 over x and square it, and then add 3 to the result. And that's exactly what I've written here. The other composition we could compute is g of f of x. And again, it's a similar process. So if I'm computing g of f of x, I plug in what f of x is inside of the parentheses of g, and then I do what g says to do. And g is the function that says take your input and put it under 1 in a fraction. Divide it. Divide by it. Divide 1 by it. And so what do? Well, I have this x squared plus 3 inside the function arguments for g, and g is the thing that takes its argument and puts it I call it downstairs. And that's it. So this is important to realize that composition is what we call a non-commutative operation. If you compose functions in different ways, you get different functions, as we just observed. So that's it for section 1.1. See you next time.